Testing.
It works.
You want to see the stream? I can see it later. It's fine.
It works.
Don't worry about the stream. Perfect. Yeah, but that would be ideal.
Do you want to try the mic?
Yes, try to turn it on.
But I don't know where it will be fed.
Me neither. Hello.
C'est la répète. Trop de monde pour la répète. Après, ils vont s'endormir à ta soutenance. Ah, t'es en train de streamer en plus.
Yes, it's streaming.
Ah, tu essayes vraiment de répondre avec
My father is watching.
c'est un mic.
Big deal.
Bah, Elliot, c'est en 4 tiers.
Ah, c'est vrai, ça. Tu sais que tu peux changer le thème pour mettre en 16 nouvelles.
Fernando,
Yeah?
look at your screen. You don't want to put it wide?
69.
I can't.
1, 2, 3,
Yes, you can.
Ah,
1, 2, 3, 4.
est-ce que tu peux chanter?
Fuck, I can't make a straight line. There.
It's freaking out.
Slightly, yeah.
Close your eyes. There's a mute button.
No, I can do it, bitch.
There's a mute button. You need to unmute.
Okay, remove it.
At least you're with them.
Non, c'est...
Testing. No.
Plus près, plus près.
Testing.
You
Sounds
have to, it's direction.
Put it here.
Testing.
Yeah, great.
better.
Cool.
You can put it on the other side.
Yeah.
The way you put it.
It's directional, so you have to.
Even better.
Ah,
Yeah,
So
further,
that's,
yeah.
Testing. Okay, let's do it.
Il faut pas que je me mette là.
Ouais, Monsieur le Président.
Yeah, can you please introduce me?
Donc nous sommes ici réunis pour écouter M. Fernando Mendonça qui nous présente ses travaux sur Multipurpose Efficient Resource Allocation for Parallel System. M. Mendonça, vous avez 45 minutes.
Okay.
C'est à vous.
Stop laughing.
C'est parti,
Hello.
en fait.
Hello, everyone. Thank you all for coming. It's a pleasure to present to you my PhD work. Okay, these are... okay. I don't think I'm saying anything about this. Okay.
We still have the diacritics issue.
That is true. I have to fix that. Okay, so this is the outline of my work. I will make a small introduction. I will describe and explain, to some extent, two of the contributions that I did during my PhD, and I will finalize with a conclusion. Okay, so I will start my presentation by talking about the platform. I put here a picture of what a tree-shaped platform looks like, and I'm going to talk about platforms that have many levels that go from cores on the same processor that are very close together to groups of clusters separated from miles and miles, groups of clusters in different regions. Okay? So the objective for us is to make this platform available for users to run their experiments and their simulations. That is what we would like to do. And the big question here is how to schedule these experiments and simulations. Where and when to run jobs that are submitted by the user. where is important because, as you can see, we can intuitively say that it's more interesting for the user if the user is using processors that are close together than if the user receives processors that are very far apart. One processor that is in one part of the platform and one processor that is on the other side of the platform. The next important question is when to run the jobs. So the users are submitting jobs and we want to know when these jobs will start, when they will end, in what order they will execute, so on and so forth. Okay. So the first idea that I'm going to introduce is the idea of a first come, first served schedule. It's the idea that the first users who submit the jobs have their jobs executed. It's the most basic scheduling scheme. Each job receives a part of the platform with the desired number of processors. And one downside of this scheme is that it shows underutilization. It means that sometimes processors are available, but they cannot be used until much further. So this is a small example. We have some jobs being submitted and they start executing. Okay, and then next, a big job comes. It's waiting because it needs all the processors on the platform. And after that, we receive one more job. It's a small job that maybe could start executing now, but it can't because it's a first come, first served scheduling scheme. Okay. The next idea that I'm going to introduce is the idea of online allocation of sequential tasks. Okay. The idea here is that when tasks of different sizes are executed, something interesting can happen, where a big task, in this case the red one, is already executing, and small tasks that are submitted later in the schedule are all required to wait for a long time. Okay, we can say that this scenario is particularly bad for metrics that consider the time that tasks stay in the system in regards to their size. So what I mean by this is that we want to measure how much time tasks have to wait. But not only that, we are thinking here that maybe for a big task to wait for some time is okay, but for a small task that could be executed quickly to wait for the same amount of time is not okay. So ideally, we would like small tasks to wait for a small amount of time, and we would allow bigger tasks to wait for a bigger amount of time. Okay, that's what I mean. Okay, I'm going to briefly introduce the metrics that I'm going to use during my presentation. At the top, we have a small picture with all the notation. We have the release time of the job when it appears in the system, the starting time of the job, the processing time of the job, the completion time of the job, and this difference below is the time the job stays in the system, or the flow time. So here we have the flow time, how long tasks stay in the system, the stretch, how long tasks stay in the system relative to their size. So this metric is proposing the idea that for a small job to wait for a small amount of time is okay, and for a bigger job to wait for a bigger amount of time is also okay. And last, the bounded stretch. The bounded stretch is very similar to the stretch, but here we are disconsidering, for the purpose of the metric, tasks that are smaller than a certain amount of time, in this case 10 seconds. Okay, so with this in place, I will start talking about the first of the two contributions, which is online scheduling of independent tasks. Okay, so what is the context of this contribution? In this case, we are interested in the problem of scheduling independent and sequential tasks without using the preemption technique on multi-core parallel machines. Okay? The goal of this contribution is to determine good solutions that can run in short polynomial time. The scenario we consider is realistic online scenario where tasks are only known to the system after they are submitted, but not before. Okay? In this context, objectives like the maximum completion time, they have no concrete meaning, and the reason is that they depend on the maximum solution time. So a small note in this case, even if we have considering maximum completion time a very good solution. If we take the solution and add one more task that is submitted later, then this task is going to dominate the metric and not the solution that was before considered good. So for this reason, we consider stretch, an objective that is based on flow time and indicates how long tasks stay in the system in respect to their processing time. Okay. So what is the main idea of this contribution? The main idea of this contribution is to detect tasks that have a negative impact on the other tasks that are waiting in the queue. Then what we can do is we can redirect these tasks to a separate pool of processors that is dedicated exclusively to running redirected tasks. Also, an important note is that we would like to start these redirected tasks as quickly as possible. The reason is these tasks have already waited for some time when they were executing in the main set of processors, and then we redirect them, and after that we would like them to not wait for much longer and start as quickly as possible. This operation is done online, as I said, and the execution of redirected tasks is restarted so that no non-preemptive assumption is satisfied. Okay, so I'm going to define the problem I'm talking about. So in this case, an instance of the problem is a set of m identical machines and n tasks. For each task, we have a release date and a processing time. The goal in this case is to find a non-preemptive schedule that minimizes the total bounded stretch, as I explained before. Yes, so here we have the same picture with all the relevant points in time: the starting time, the completion time, and the flow time. Okay, I'm going to now do a small explanation of how redirection works. We have a schedule that starts with a big task that is submitted at time 0. Okay, then at time 1, a small task is submitted. Okay, at time 2, another small task is submitted. We can see here that this is the negative impact that I was talking about is happening. Now, 2 small tasks are waiting for one big task. Okay, then a third task is submitted, and we have small tasks until 6. In this case, we have p small tasks, and we can see that each small task in this schedule has a flow time of p. And the reason for this is that each small task stays in the system for p amount of time. The first one, for example, finishes at p plus 1 and was submitted at 1. The second finishes at p plus 2 and was submitted at 2, so on and so forth. If we compare that to the offline optimal solution for the same instance, we can see that as soon as the small tasks are submitted, they start executing. So we execute all the small tasks, then we execute the big task. In this case, each small task has a flow time of 1, because, for example, the first task finishes at 2 and started at 1, so on and so forth. So we can see here that there is a ratio of p between the offline optimal solution and the online solution that we were talking about. Okay. Now the next question is, what would happen if we could redirect the big task and run it elsewhere? Okay, if that were true, if we could do that, then we start in the same way. We start with the big task, then we receive one small task, and we think that okay, so far it's fine. It does have a negative impact, but it's only on one task, so we continue executing. We receive a second task, the impact grows stronger. We think that that is still fine, and we continue executing until we receive a third task. So when we receive the third task, we might decide that it's too much, that the impact is too big on the small tasks, and we decide to redirect the big task. When that happens, we can start executing the small tasks from this point. And then we have the 3 small tasks that were already submitted and the remaining after. So in this case, we can see that each small task has a flow time of 3. For example, first one was finished at 4 and was submitted at 1, hence 3, so on and so forth. So It's a flow time bigger than that of the offline optimal solution, but much smaller than the original solution. Okay, so in this case, to use the redirection scheme, we need a few things. The first thing is the parameters. So we have the tau, which is the redirection constant. It means how many small tasks need to be affected before the big task is redirected, and the set of dedicated machines. How many machines we are removing from the original set of machines to become dedicated machines. So the steps are, first, reserve the dedicated machines, then at the beginning of execution of any particular task, set a counter equal to 0. That's the redirection counter. Okay? Then, whenever a task with a processing time that is smaller than that of the original task, increment the counter by 1. If that counter reaches the tau redirection constant that I defined earlier, then we interrupt and redirect the task. Okay, a couple more details. The first one is how do we schedule tasks? So whenever a machine is idle, we choose the smallest task to start executing. That's the smallest processing time scheme, and this is the optimal solution on a single machine for the flow time objective, so that's the one we use. The second important aspect is how do we deal with the queue of the machines. Each machine has a queue. Each machine has one executing task and a queue. So we have one queue per machine, and whenever a task is submitted to this machine, submitted to the system, we add it to the queue of the machine where the increase in the objective would be minimal. So we have machines. We are considering on which machine to add a certain task. We check for each machine what would be the increase in the objective, and we pick that where the increase is the minimum. That's it. Okay. Now we want to compare this redirection policy to other policies that are interesting. The first one is the basic one. The SPT is smallest processing time. In this case, there is no redirection, and all machines are used. So if on one side there's no redirection, there's no way to adapt to the tasks, all machines are used. So this policy doesn't have to separate machines. It has more machines to use. The second one is the random policy. In the random policy, whenever a task is submitted, we select a number at random uniformly in the 0 to 1 range. If this number is smaller than a certain constant, we redirect the new task to the set of dedicated machines. The positive aspect of this policy is that it does not waste time running a task that could be redirected early. It makes a decision as soon as the task is submitted. The downside is that it doesn't choose particular tasks. It can redirect a small task and it can redirect a big task. So we would like to know how it compares. The last one is the smallest remaining processing time policy. This is a policy that uses preemption. So in this case, if a task is causing a negative impact on the schedule, it is removed from the schedule and added later in the same machine. And it provides a two-competitive solution for minimizing the sum stretch objective on a single processor. So it's at most 2 times worse than the optimal solution. And for that reason, we would like to compare it to our rejection policy. Okay. Yes. So, in order for us to run the experiments, the simulations, we acquired some traces from the literature. Here we have the place where we took them. Here we have the traces that we chose and the original characteristics. In order for us to choose to use these traces, we need to first transform them. We need to transform the parallel jobs inside those traces into sequential tasks, which is what we are talking about. And we do that while keeping the work ratio. Furthermore, for each trace, we generate 20 random instances. Here on the second part of the table, we can see the characteristics of the instances. We can see the new number of processors, the new number of tasks, and then the number of days that each random instances lasts. Okay. The first graph that I'm going to show is the one for some stretch. We have on the x-axis the different platforms, the different traces. We have on the legend the different policies, and on the y-axis the objective, some stretch. We can see here that the redirection policy that we are talking about shows very good results, much better than random and SPT, and even approaches sometimes the performance of the SRPT policy, which we consider in this case a lower bound. That is the case for most platforms. Next, the same thing, but for the max stretch objective, we have the same characteristics on the graph, and we have the same results. We have redirection that shows results that are much better than random and SPT, and sometimes get even close to the SRPT objective, SRPT policy. Okay. This is a small comparison between stretch and flow. So I was talking about the two at the beginning, and I was explaining that stretch focuses on the size of the task. So for flow, the size of the task doesn't matter, and for stretch, it does matter. So here we have, for example, the SPT policy, which shows the best result for flow. And the reason for this is simple to explain, is that SPT doesn't have to compromise machines in order to run the schedule. So because it has more machines to use, on average, all tasks will wait a little bit less. But the consequence is that the stretch is very bad. And the reason for this is that small tasks are waiting on average as much as big tasks, which is very bad for stretch. Okay. Something else that I would like to point out is that the redirection policy here has a more stable result. It shows good results both for stretch and for flow. So on average, tasks will not wait for much longer than SPT, but if you consider the size of the tasks, then it shows very good results for stretch. Okay. The last graph that I will show on this section is this analysis of the flow time for one of the platforms. Okay. So on the x-axis we have the thresholds, the redirection constant that I showed before, okay, from 2 to 10. On the division we have the number of dedicated machines, the number of machines we are separating from the original set. Okay. On the y-axis we have the flow time. On the green part of the bar we have the flow time coming from the dedicated machines, and on the blue part of the bar we have the flow time coming from the standard machines. As we can see here, as we increase the threshold, we can see that the flow time on the dedicated machines increase because we have less and less tasks being redirected. So on average, each task has to wait less. On the same side, if we increase the number of dedicated machines, we have more resources to work with, and then we have a smaller amount of waiting time. Okay. The other point I would like to make is that on the other side of this equation, if we do the same thing that I was talking about, if we increase the threshold or increase the number of dedicated machines, then we have less resources to use on the original set of machines. For that reason, we can see that the flow time from those machines increase. So we didn't continue running the experiments with bigger values, but we can extrapolate and expect that if we did continue, we would see the flow time for the original machines increasing. Okay, that concludes the first. Didn't exist? You didn't see anything? Let me drink some water before I start the next one. Okay. So I'm going to start the second contribution that I would like to talk about, and the subject, it's about the scheduling with backfilling and locality awareness. Okay. So the motivation for this contribution is that HPC systems are evolving very fast. Additionally, we can say that processing power is increasing at a much faster rate than I/O and interconnection capabilities, which could lead to contention and latency-related issues in some cases. Then, if we combine that with platforms using several levels of hierarchy, as I showed in the beginning of the presentation, the difference in latency and bandwidth across levels is significant. Then, with all this, it becomes crucial, it becomes very important to analyze how jobs are allocated on the available processors. So, introducing the backfilling algorithm, we have a schedule here that is the same as I showed before for the first come, first served processing scheme. But the difference is, first, users are asked to submit estimated runtimes for their jobs. So when they submit jobs, they have to say how long they expect their job to take. Okay? This information is used to reserve the time, to create a reservation for each job on the schedule. Now, with this information, we can move small jobs forward in the schedule and use space that was left by other jobs. So here we can see on the figure that we had jobs executing, we had a big job that is waiting to execute later, and then after we received job number 6, it was able to move forward because there is enough space for it. And we use that space because we have an estimated runtime for this job. We know that this job will not last long enough to conflict with job number 5. Okay, some extra notes about backfilling. Jobs can be killed if they underestimate their runtime, and can lead to underutilization of the platform if they overestimate. So on one side, if the user underestimates the runtime of their job, the execution will reach the point where the job was supposed to finish. Maybe one other job is starting. So this job has to be killed. On the other side, if the user overestimates the runtime of the job, it means that the job will finish quickly, and then the platform or the resources will be occupied for a long time, not being used. The second note is that backfilling works very well by its own, and it's consequently hard to improve if there is no significant latency between the processors of the platform. So if all the resources on the platform are similar, and the communication between all of them is the same, then it is true. It doesn't matter where the resources are allocated. But if that is not the case, then backfilling performs poorly. If the latency between some of the processors is significant, if some resources are too far from other resources, then backfilling performs poorly. And the reason for that is that backfilling does not choose specific processors for each job, but rather picks the first ones available. So if we do have processors that are far away from each other, backfilling could very well choose half the resources on one side and half the resources on the other side, which would cause most of the communication to go through this path that we think is slow and should be avoided. Okay, the next aspect of backfilling that I would like to explain is how backfilling works. Okay, so in order for backfilling to work, it needs a few things. First, it needs to reserve time for jobs when they are submitted using the user submitted expected runtime. And the next thing that backfilling needs to do is be able to free space when jobs finish early. Okay. Okay. So I have here a figure that shows how backfilling does that. So backfilling uses time slices. Time slices are points in time in the schedule. Each time slice has a starting time, a duration, and the list of available processors. So we have the first time slice that starts at time 0, has a certain duration, and has one available processor. The second time slice starts at when time slice 1 finished, has a duration, and one available processor here and one here. So on and so forth. If we have this data in place, then when a new task is submitted, and when a new job is submitted, we can verify on which time slice the job could fit into and prepare a reservation for that job. Okay, so if time is right here, right now, if this is the now, and a new job is submitted that could fit in here, we could use this data structure to make a reservation for the job here and start right now. Okay. The next important thing that we implemented with backfilling is the notion of job reassignment. Okay, so as I was saying, when a job finishes early, we want to reutilize the space left. We do that by removing the remaining space. Pause. Let me see. Okay, we'll unpause. It's focused, right? I have no idea. Ah, it's a dot. Okay, now it's a dot. Okay, so we do that by first removing the remaining space used by the job. So a job finished early. It was supposed to last 10 hours and it lasted 7 hours. So we take these 3 hours and we remove it from the schedule. Then for all the other jobs that are in the queue, in this case jobs 3 and 4 in the picture, we remove the job from the schedule, in this case 3. Then if there is enough space for this job to start right now, we schedule and start it. If there is not, then we reschedule it to its original reservation. So in this way, when a job finishes and frees up space, we look at the time slices, at the data structure, and see which jobs could maybe be advanced and start right now. So here we have job number 3, job number 2 finished early, and job number 3 was able to move. You see that job number 4 did not move. That would be an operation that we would like to leave for later. So job number 3 started right now. Okay. Now job number 1 finished early also. Then job number 4 is able to move forward and start right now. Okay. Now I'm gonna explain the different constraints that we apply to backfill. So I was explaining that backfilling by itself does not choose processors. It just picks the first ones available. So we would like to choose processors, okay? And we implemented a few different ways to do that, and we would like to compare them. So this is not having a constraint. This is basic backfilling. So given a starting time and a list of available processors, pick processors until we have enough for the job, until we have size J. So here we have an example of a platform. We have in green, in this color, the CPUs that are available, and in red, the CPUs that are not available. Okay. Suppose we need 4 CPUs. Since this is basic backfilling, we pick the first 4 CPUs that are available. Now I colorize here on the platform the nodes, the interconnecting nodes that we need in order to execute this job. So because we are utilizing these processors, we need these interconnecting nodes. This means that the communication, in the worst case, has to go through all the nodes of the interconnection until the root. The next constraint that we'd like to talk about is contiguity. So with contiguity, we start with the same thing. We start with a starting time and a list of available processors. We sort the contiguous blocks by size, by decreasing size, and we pick processors from the blocks until we have enough for the job. So we have the same example. We have 2 contiguous blocks. We have one here of size 1 and one here of size 6. So we start with the biggest one and we choose 4 processors. In this particular case, we can see that the same thing happened as before. We chose the biggest block, and consequently, we are still using the nodes of the network until the root. The next constraint I would like to show is basic locality. Okay, basic locality, it uses the abstraction of a cluster. Comment in this slide should have a line here showing that each cluster is this last level. So this is a cluster, this is a cluster, this is a cluster, and this is a cluster. It will be in the final slide. It should be here. Okay. So we have here 4 clusters. Then giving a starting time and a list of available processors. Sort the clusters by size, by the number of available processors in the cluster, and then pick processors from the clusters until we have enough for the job. So in this case, we have 4 clusters. We have 3 clusters with 2 available processors and 1 cluster with 1 available processor. So we pick clusters from the beginning until we have enough. So in this case, we have 4 clusters, and the same thing happens as before. The same thing can happen as before. In here, we are using the network nodes, and the communication is, on the worst case, going through the nodes until the root. The last constraint that I would like to show is the constraint of platform level. So in this case, we start with the starting time and a list of available processors. But in this case, we go through the levels one by one, starting from the lowest one. And for each node at this level, we check if enough processors are available for the whole job. If yes, select processors until we have enough for the job. If not, we go up on one level. So in this case, we start at this level here, which is the last level where we can connect processors. So we look at all the nodes of the level. We look at first at this one. Does it have enough processors for the job? We need 4 processors. No, it does not. Does this one have? No. Does this one have? No, and no. So no nodes at this level have enough jobs for the enough processors for the job. So we go up one level. So we look at this node. Does this node contains below it enough processors for the job? No, it has only 3 and we need 4. So this node, does this node contain enough processors for the job? Yes, it has 4 processors. So we select these processors, and if we colorize the network nodes, we realize that now we are using one less level. Okay. In the worst case, the communication between the processors allocated will go 2 levels. Is the microphone okay?
Yeah.
Okay. Okay. So now, how do I compare these constraints? The way that I chose to compare these constraints is by analyzing how often jobs fail and succeed. Okay, so users, they submit a job with an expected runtime, and the job also has a real runtime that is equal or smaller than the expected runtime. When processors have been chosen for a job, the new runtime is calculated. This is the I'm going to start this slide over. Okay, sorry, this slide's new. I don't know how to explain it. Okay, so how do we compare these constraints, and how do we analyze which one is better in this scenario or that scenario? The way we do it is using an overhead model. It's a way to assess on which constraints the jobs have better or worse execution. So when processors have been chosen for a job, we can calculate a new runtime. Okay. I have no idea how to explain this slide, honestly. Because this is so weird. Yeah, but reading doesn't make sense either. I tried. Multi-factor. Yeah.
Just actually reword the slide probably.
Yes, I have. I need to make it again. Yeah.
Don't waste time on it right now.
Yes.
You also want the time.
Yes. I have 10
Anyone
minutes.
check the time?
35, I have the clock. Restarting. Thank you. Continue. Okay. 35, 40. Before I start showing the experimental setting and the results, I would like to mention some additional metrics that I use to compare the constraints. The first one is the contiguity factor. So contiguity is one of the constraints that I mentioned, and the contiguity factor for a certain job is the number of contiguous blocks used by the job. So if the job is using 1 block, it means it is contiguous. So it has a contiguity factor of 1. If it's using 2, then 2, and so on and so forth. The second one is the locality factor. The locality factor is the ratio between the current number of clusters used by the job and the minimum considering the size of the job. So if the job has size 8 and each cluster has size 2, the minimum number of clusters the job can use is 2. So if the job is using 2, then it is using the minimum, and the locality factor would be 1. The third one is the platform level factor. It's the same, but for the platform level. It's the ratio between the number of platform levels used by the job and the minimum considering the size of the job. The last one is the job success. So the job success for a job is 1 if the job finishes before the end of the reservation and 0 otherwise. Okay. As in the previous section that I was talking about, here I use the same platforms and the characteristics are the same. The difference here is that in this case I don't have to do any transformation. I can use the trace originally in its original form because I am scheduling parallel jobs. Okay. The only thing that I do is that I also want 20 random instances. So I do it in the same way as before, and here we have the number of weeks that each instance lasts for. The traces are downloaded from the same place. That's this. Okay. So this is the first graph. This graph is showing the sum flow, and here on the legend we have the different variants. So in gray we have basic, then we have best effort contiguous, best effort local, best effort platform, contiguous. I know that I forgot. He's writing that I forgot to explain best effort and yeah, I forgot, I know. Contiguous, local, and platform. Okay? So I will focus on the Coheed platform. Okay? So we can see here that almost all the variants showed results similar or better than basic. And I would like to point out that best effort platform and forced platform showed very good results for some flow. Okay? Best effort platform showed the best result among the best effort variants, and forced platform showed the best results among the forced variants. Okay? This result is consistent in most of the platforms. Next, for the contiguity factor, I would like to point something out first. So we can see here that the best effort contiguity and the forced contiguity show the best results for contiguity factor, which makes sense because that's the main objective of the constraint. And next, I would like to point out that although that is true, best effort platform level and forced platform level showed good results in comparison to the other constraints. That is also consistent in most of the other platforms. The same thing for the basic locality constraint. Okay, so we can see that the best effort local and forced local show the best result because that's the constraint that these variants are trying to optimize. And I would like to point out that considering that, best effort platform and forced platform showed good results when comparing to the other constraints. It's also consistent. Next, for the platform level factor. And this, we reach the point where we can see that the best effort platform and forced platform show the best results because that's exactly what we are trying to achieve. We are trying to reduce the number of levels used by each job. That's it. We're trying to reduce the number of levels used by each job. The phrase finishes there. Yes. The last graph that I'm going to show is the job success rate. So as I explained before, for each job, we want the job to succeed. We want the job to finish before the reservation time ends. And we know that where the job is placed in the platform affects that. If the job is placed in a part of the platform where the communication is low, there is a higher chance that the job will not be able to finish before the reservation ends. On the other side, if we place the job close together, there is a higher chance that the job will finish its execution before the reservation. And this is what this metric is about. We count how many jobs in the schedule succeed, and these are the results. So we can see here that almost all variants have better results than basic, which is what we expect. And I would like to point out that best effort platform and forced platform show the best results for the number of jobs that succeed. It's also consistent in most of the platforms, if not all. Okay, so now I'm going to do a small conclusion that is not done yet. That's it. 41 minutes with the more than conclusion. Okay. Now, I would like you to ask me, what was the question? How do I convert the parallel jobs into sequential tasks? It's a backup slide that I will not explain unless someone asks me. Because you see how it looks like? It's a mess. So ask me. No, it's just that it's technical information that is not really relevant. But if someone says, how do you do this transformation? You didn't explain. And then, okay, so I will explain if you want me to.
You wanted me to explain.
Yeah, you are.
The formula.
Okay, so you are asking how do I convert parallel jobs into sequential tasks? When we were working on this contribution, we prepared 3 methods and we chose the third one. Okay, so the idea is each job is characterized by a real execution time, a number of required processors, and a release date. This is not part of the 45 minutes because it's a question. Method 1, for each parallel job, create QJ sequential tasks, each one with processing time EJ. So we are breaking the job and creating one parallel task, one sequential task for each processor the parallel job uses. The second method is, for each parallel job, create one sequential task with the processing time that is the processing time of the original job times the number of processors used by that job. So it's one task that uses one processor that is much longer. The third method is the following. Okay, so Q is the average number of processors used by all the jobs in the random instances in the random instance that is being constructed. Okay, for each parallel job in this instance, create one sequential task with a processing time that is the original processing time of the parallel job divided by this average, multiplied by the original runtime of the job. Yes, that's it. Additionally, the number of processors used for the instance is the average, is the number of processors available in the instance originally divided by the average. Not the average, but the original divided by the average. And that's it. That's how we try to reduce the size of the trace, reduce the number of processors, transforming the parallel jobs into sequential tasks, but attempting, to the best of our knowledge, to keep the work ratio of the instance that we created from the parallel jobs. That's it.
Mic drop.
Thank you. Ah, here, okay, got it.
On off.
Thank you.
Just push once and it's okay. Just push on it. Yeah. If you have questions, you have
If you don't shut it off, it's okay. We will empty the battery for tomorrow.
You have to hold it. You didn't know it.
Ah, c'est ce que le chargeur est à la ça marche quand même pas.
the push. Good boy.
Okay, so do you have any questions, like questions that you really have about the holes in the presentation? If you have, feel free to tell me. 41.
Go to slide 1.
Wait.
Just go to 41.
He's the biggest troll here.
Go to the last one.
Last one? Okay.
Yeah. It's fresh in the middle. Correct me if I'm wrong. Method 1, you have the same runtime.
Yes.
Method 2, you have the same work amount.
Yes.
Method 3, you keep the work ratio. Why
Yes.
don't you say that?
Maybe I could, yeah, but I thought it was obvious because
Then why don't you write that? Method 1, double
Yeah,
dot,
method 1, you
blah
column,
blah blah.
Sure.
runtime. Method 2,
Sure.
same work. Method
Sure.
3,
Suggestion accepted. Yeah, thank you. That's
Okay,
good.
slide 1.
No, not slide 1.
Okay.
Like the accents are missing. I'm going to put them later because when I was writing this, I was on a computer that could not write accents. Real stories. Bouvry and Navo are the ones that reviewed the thesis. I'm not sure who is the president actually. I have no idea.
You are missing letters, not only act.
Okay. I will fix the French. I promise.
No. Fix it now.
Okay, sure.
The title slide, the one who stayed decades on those.